All right. Class 2 days from now, so on Friday the 25th, I'm going to have a recorded video for you to watch. And then we'll be back to a live in-person class meeting the following Monday. So speaking of Friday, that's when phase 2 of your design project needs to be submitted. And what you're submitting specifically is 2 PDF maps. And I don't need the files from Water Gems. Don't need them and don't want them, frankly. I just want the annotated maps. And so one of the maps shows what your system does at the design condition, which means maximum flow rate, so that full demand that you've calculated in phase 1. And then the other map is showing what your system looks like, meaning in terms of the pressures, with zero flow. So pay special attention to that you've got all of the annotations. So the handout describes, for example, that you need to have the pipe diameter listed, the junction names, the pressure at each junction. So be sure that you've got the annotations correct. So you submit that by 1 o'clock on Friday. And then the next assignment, homework number 10, which is posted on Blackboard right now, it should be submitted by 1 p.m. on Tuesday the 29th. And the reason for that strange submission time is that then you have an exam the day later. So at 1 I'll have the solution become available for homework number 10, so that gives you a day to look it over before we have the test on Wednesday the 30th. And so for that exam, it'll follow a similar approach to the first test where I provide you with the formula sheet, and then this one's going to be covering from lectures 19 through 29, and you can bring in 1 page of your own notes. And so, for example, if you want to refresh your memory on how to apply the specific energy technique or how to draw a specific energy diagram, just whatever things you'd like to include in that single page of notes, front and back, letter size, then you're welcome to do that. Any questions related to these announcements? All right. I've had a few people stop by to discuss their demand estimation phase 1, and I'm happy to have those conversations. If you have any follow-up questions, like if something wasn't clear in the comments that I typed in phase 1 for you, feel free to stop by, because I've got my own calculations for what I think the flow rates should be based on a kind of some middle-of-the-road assumptions. And so if you're still not quite sure how to make some adjustments, then by all means, please stop by. All right, we're going to continue talking about open channel flow, and what we're trying to do is we're trying to predict what is the depth when conditions are not steady and uniform. And specifically, it's non-uniform flow that we're looking at. We're looking at what happens when there's some obstruction downstream. And when there's no obstruction, remember, what equation can we use when it is steady uniform flow? I asked the same question on Monday. Manning's equation. Good. All right. Maybe I'll ask this every class. Manning's equation only applies steady uniform flow. But when it's not steady and uniform, like we worked this example on Monday, and the reason why this was non-uniform flow is that the water was moving along at a depth of 10 feet, but then someone dropped an obstruction that was 10 feet tall. And what we learned in that example from Monday's class was that the obstruction height was above what can be allowed. There is some delta Z max that can be tolerated. And if there's not enough energy upstream to get over the obstacle, then pooling occurs. And pooling is the increase in water depth until there's just enough energy to get over the obstruction. Now, who can remind us, why does water flow over the obstruction at the critical depth? The water doesn't think, so it's not making the choice to flow over the obstruction at the critical depth, but there is still a reason why it's flowing over the obstruction at the critical depth and not some other depth.
Least amount of energy?
Because that's right. He said least amount of energy. And so what it means is the most efficient flow depth the flow depth that's able to convey the flow, Q, with the least amount of energy required, is the critical depth. And so the E minimum, E min, is 3/2 times Y sub C. That is, remember, energy is in two places. It's in the depth and the velocity head. And it just so happens that when you're at the critical depth, that the velocity head is 1/3 of the specific energy, and the depth is 2/3 of the specific energy. Okay, so the water didn't initially have enough energy upstream to get over the obstruction, and so it pooled until there was just finally enough energy to get over that obstruction, and the minimum amount of energy that's required corresponds to the critical depth. All right, so that's just kind of a conceptual review. Now, let's put that to practice and do this assessment of, will the flow choke if the obstruction is 3 feet? So we know it will definitely choke if it's 10 feet. This is that same scenario. 500 CFS flow rate, a rectangular channel that's 10 feet wide, an initial upstream depth that's 10 feet. So in the previous illustration, we saw that a 10-foot sill is too tall. That 10-foot sill will cause choking and pooling. But will a 3-foot sill cause choking? So for part A, what we're going to do is we're going to see how much energy is there available at 1 and compare that to how much energy is needed at 2 to get over the obstruction. So let me just put some of these previous things that we've determined here on the whiteboard. What we had calculated in that prior example, previously, we got the Y sub C. And just to back up a step, remember that the critical depth for a rectangular channel is the flow per unit width squared divided by G to the 1/3 power. And you're always remembering in your mind, this only applies for a rectangular channel. It wouldn't work for a trapezoidal channel. So from that, because we know we've got a 10-foot wide channel, so B is 10 feet, and we've got this Q of 500 CFS. So the Q, flow per unit width, is 500 divided by 10, 50 feet squared per second. So we put that into the formula for Y sub C, and we got it was 4.265 feet. Okay, so that's the critical depth. And what we can see is what is the minimum energy, E minimum, and that is 3/2 Y sub C. So 3/2 Y sub C, let me do that calc. Oh, I've got it here on the page. 6.398 feet. Now let's see how much energy is available at 1. Because if the energy available upstream is greater than the minimum, then no choking will occur. That's kind of the if-then that we covered in Monday's class, is comparing the required energy to what's available. So this is how much energy required. Let me just write this on the board. Energy required at 2 for flow at critical condition. All right, so then what about our E available? So we're talking about available at 1. How much energy is there? So remember, the energy is in two places. It's in the depth and in the velocity head. And so it's going to be y1 plus, and there's lots of different ways for us to calculate the velocity head. Let me just jump ahead briefly to remind you that we've seen it could be v squared divided by 2g, we can calculate the velocity head by q squared divided by 2ga squared, or this new one, flow per unit width squared divided by 2g y squared. So in the case that we're looking at right now, let me just write it in terms of q squared divided by 2ga squared. Okay, so our depth at 1 is 10 feet. And that alone tells me we've got enough energy. Because look, the minimum that's required is 6.38 plus the 3, because the amount of energy that's at 1 is going to be subtracted by the step height. So 10 plus the velocity head gives us 10 and change, minus 3, so that's going to be 7 and change, so that's more than minimum. So I already have a good feeling that this is not going to choke the flow. But let's go through and do all the calculations. Okay, so that's the depth. The depth alone has enough energy. Let's add in the velocity head. So 500 CFS squared divided by 2 times 32.2 feet per second squared. So that's our G. And then the area squared. It's 10 feet wide and 10 feet deep at 1. So the area is 100 feet squared. And I square that. So the energy available at 1 is 10.3882 feet. Okay, so there was 10.388 feet of energy here. There has to be 6.398 above the sill, and the sill itself has a height of 3 feet. So let's just do like the full expression of all of the energy that there is. There's the 10.388 minus 3 feet for the sill is equal to our new depth at location 2, because we don't necessarily know what the depth is going to be at 2. It's going to be y2 plus 500 CFS squared divided by 2 times g, 32.2 feet per second squared, times the area squared, 10 times y2 squared. So this is like all of the energy accounted for. The energy at 1 minus the step up is going to be how much energy there is at 2. So this is the specific energy. The energy above the sill is going to be the depth and the velocity head. So once again, we find ourselves needing to solve a cubic equation. We can just maybe break this down a little bit further. It is going to be 7.3882 is equal to y2 plus 38.82 divided by y2 squared. You know, like if you do the 500 squared divided by 2g, 10 squared. Okay, so we get this. And we're going to need to solve for y. Let me bring my chicken scratch notes up on the screen for the benefit of those who may be following along remotely. All right, so we're at this point where what we've done is we've said there's the depth at 1, the velocity head at 1, subtract out the sill. That's basically just like an obstruction, a vertical obstruction, a block wall that's in our channel for some reason. Has a height of 3 feet, so we subtract it from the energy at 1 because that 3 feet of energy is not going to be available as specific energy at 2, because specific energy measures how much energy is in the water above the bottom of the channel. And at 2, the bottom of the channel is the top of the sill. Okay. So we can rearrange this further. Here's y2 cubed divided by 7.3882 y2 squared plus 38.82. We got that just by multiply each of these terms by y2 squared. Okay, and then this is where I become kind of a fan of Wolfram alpha as a method of finding the roots of that equation. Okay, so natural language, yeah. All right, so it is y cubed minus 7.3882 y squared. Of course, you can do this on your Casio or whatever other calculator you're using. Y squared plus 38.82 is equal to 0. All right, and it finds 3 roots for us. A negative root, which we're not very interested in because water doesn't flow at negative depths. A positive root, which is corresponding to the supercritical conditions, and a deeper depth, which corresponds to subcritical. Let me ask you, in these calculations done so far, I didn't specifically call out whether the flow is supercritical or subcritical at location 1, but we have everything we need to make that diagnosis of the flow regime at 1. We could either calculate the Froude number, or what's the other way? We sometimes determine if the flow is supercritical at 1 or subcritical at 1. That's right. Good. So you compare the depth at 1 to the critical depth. And so what we had initially was the depth is 10 feet, and we know the critical depth is 4.2. So if the upstream depth is more than the critical depth, what does that tell us about the flow regime at 1? Subcritical. Good. Yeah, so then if it was subcritical at 1, that helps us to know that we need to choose this subcritical route. So the water is going to be flowing at a depth at 2 of 6.45. So it's not even flowing at the critical condition. That delta Z isn't so big. The 3-foot height isn't so big that it's going to induce the critical depth over the obstruction. It only flows at the critical depth if there was choking and then it reestablished some new equilibrium, or if the delta Z was at the maximum delta Z. And 3 feet isn't the maximum delta Z. So any questions so far on how we applied the principles of specific energy analysis to find the new depth over that sill? You could really impress your parents with this stuff. I'm telling you, they just feel such a swelling pride if you came home and you sat them down and you said, listen, there could be an obstruction in a channel and you got to know how to calculate the new depth. And we're going to do that. You just kind of sit down at the dinner table, go through, show them, now this is a cubic equation, we got to find the roots, and hone in, explain to them how you know which of the roots to choose, and they'll just have tears in their eyes thinking about how smart their child is, remembering you in diapers, and now you're solving cubic equations. Really, I'm not joking. You should let your parents know what you've learned. They'll be proud of you. All right, so part 2 of this example is find the maximum allowable obstruction before choking. So 3-foot sill height didn't cause any choking. How high could we go and get away with there not being any choking? The delta Z max. And it's actually relatively simple. Has everybody got this stuff on the whiteboard? Let me erase this. Because we knew how much was initially available, and we know how much is required, and the delta Z max is the difference between the two. All right, so what we found is that E initially available at 1 was 10.388 feet. That was the depth plus the velocity head. And we also knew for the critical depth, YC of 4.265 feet, then E minimum, which corresponds to the most efficient flow condition under critical conditions, E minimum is 3/2 of that. 3/2 YC, so that was 6.398 feet. The delta Z max is the E available minus the E minimum. So in our case, it's basically 3.99 feet. So that obstruction could be as tall as, once it got to 4 feet, we'd see just the tiniest bit of pooling upstream. We could have a delta Z max of 3.99 feet. So that's just how much energy is left over before you get to choking upstream. Okay, so a step up like this isn't the only kind of obstruction that can occur. Obstructions can also occur when a channel gets narrower, and that's what we're going to talk about next. But before we do, any questions about the vertical obstruction? We've got an exam next week, right? Okay. Boy, these vertical obstructions are just fascinating. Can you tell how animated I'm getting about these? I just love these vertical obstructions. We got an exam next week, right? All right. There can be a step up, or a channel can get narrower. And so let's consider that. Big Q has units of volume per time, like cubic meters per second or cubic feet per second. So that's big Q. Little q is flow per unit width. So it's big Q divided by B. So even though if water is going through a channel that contracts, the flow stays the same, but the flow per unit width is different. The flow per unit width is increasing because B is smaller. So remember the definition of flow per unit width. Let me just write this on the board. So flow per unit width is Q divided by B. So if B is smaller, then lowercase q is bigger. So what we have when the channel contracts is a larger flow per unit width, and that's going to mean that there's a different critical depth as well. So if we were to draw a specific energy diagram of the upstream wide section, this, the one on the left, is the specific energy diagram for that. But if the water goes through this tapering channel that's getting narrower and there's a contraction, the flow per unit width is higher, so the critical depth is bigger. So here, see how they've got the YC before the contraction, and then here what they're calling the Y prime C is what was the critical depth after the contraction. So that pushes the specific energy diagram to the right and then also upward. Now it pushes it to the right because there is more specific energy for a given depth, but it pushes it upward because of the increase in the critical depth. So the new E minimum is larger because, remember, we've said that E minimum is YC times 3/2. Because at the critical condition, depth is 2/3 of the specific energy. Velocity head is 1/3 of the specific energy. So if we know that the depth itself is 2/3 of the specific energy, we can calculate the entirety of the specific energy by multiplying by 3/2. That is 2/3 times 3/2 equals 1. So minimum specific energy goes up because the critical depth goes up. So that's if a channel contracts. Now this is that slide I showed you earlier today where we were just kind of reviewing the idea that velocity head can be expressed in terms of velocity or flow rate or flow per unit area, flow per unit width, excuse me. And that specific energy is looking at the upstream versus the downstream. So there's no delta Z in these formulas because now we're just talking about a change in the width. So there's no obstruction. So the delta Z doesn't apply if the channel is changing its width. But this third formula is going to be pretty useful because the flow per unit width is changing. So we can use that flow per unit width, and then the only unknown is going to be the new downstream depth Y2. Okay, so in an expansion, the flow per unit width is decreasing because B is getting bigger. So I've talked about how if the channel contracts, that shifts the specific energy diagram up and to the right. So if the channel gets wider, if it expands, then that's going to move the specific energy diagram down and to the left for similar reasons, because if the flow per unit width is lower, then the critical depth is lower, so that's what shifts it down. And if the critical depth is lower, then the minimum specific energy is also less, so that's what moves it to the left. Now, when channels contract and expand, there's oftentimes going to be a loss coefficient that accounts for some of the energy that's gained or lost through that expansion. And typical contraction coefficient would be from 0.1 to 0.6. Expansions lose a little bit more energy, so from 0.3 to 0.8. But it's just that the available energy at location 2 is less than it otherwise would be if we weren't having that loss. And so the loss is added to the right-hand side of the equation. So let's get some practice with this and consider an expansion. What we know is the flow rate is 9.9 cubic meters per second. We know the initial width is 3, and then the initial depth was 2.75, and this expansion coefficient is 0.45. What if the channel gets wider? Instead of a width of the channel of 3 meters, it's now 5.7. Now, sometimes things get counterintuitive with open channel flow. Like maybe you'd expect that if it gets wider, you'd be forgiven for thinking that the depth is going to decrease. But actually, that may or may not be true depending on whether the conditions are supercritical or subcritical. And then it's also, you know, the energy that's lost through the expansion plays a role as well. So the only way to know for sure whether the depth is going to be getting deeper or shallower is to actually go through the steps of calculating specific energy analysis, comparing 1 versus comparing it to 2. So let's go through those steps. Let me give you kind of a suggested workflow, and then I'll pause and allow you to do this. First of all, find Q, lowercase q1, so the flow per unit width at 1, and then from that you can calculate the y sub c, and then diagnose the flow regime. I'm pretty sure that's not how you spell regime. Regime. Let's call it that. Super or sub? Okay. And then find E1, so the specific energy at 1, and you're going to substitute it into, well, actually actually use y1 plus q1 squared divided by 2g y1 squared is equal to y2 plus q2 squared divided by 2g y2 squared plus c times q2 squared divided by 2g y2 squared. All right, so I'll pause here. I've got the solution, but what we're trying to do is find out what's going to be the new depth downstream when we've had some energy loss due to the expansion, but then also a new flow per unit width at location 2 is going to change the distribution of how much of the energy is in the depth versus how much of it is in the velocity head. All right, so just to recap, we've got a narrow channel that expands to a wide channel. And what we know is that we can account for the specific energy and use that to predict what will be the new downstream depth. What determines the depth is how much energy there is in the water. And some of it is going to be lost through the transition. And then because the channel is wider, that's going to adjust the distribution between how much of the energy is in the depth and how much of it is in the velocity head. So that's all of what's happening in this formula. In this specific energy equation, we're saying there was some specific energy at 1, which was in the depth and the velocity head. And then at 2, there's depth and velocity head. And then also on the right-hand side of the equation, we're adding in the amount of energy that was lost due to the expansion, because it's downstream, and that energy is lost, and it is not incorporated into the new downstream depth because it was lost. All right, so we found flow per unit width at 1 is 3.3 meters squared per second. From that, found the critical depth. And since the given flow depth is more than the critical depth, then upstream the conditions were subcritical, which we keep in mind because that's going to help us to pick which root applies when we solve the cubic equation. Also getting the flow per unit width at 2. So here you can see the substitutions that I've gone through into the specific energy equation. And we've got this negative root that we throw out, a supercritical root, and the subcritical root, which is the one that we select. So we expect that the new downstream depth is going to be 2.794 meters after the expansion. So we're really getting a lot of mileage out of this specific energy idea. It's a very useful approach to figure out what is the depth when you have non-uniform conditions. Like, how does the water react when there's an obstruction, a step down, a narrowing, or a widening of the channel? All 4 of those conditions can be analyzed with specific energy. So just as one last example, to tie things up, let's look at a channel contraction. Okay, it starts with a width of 10 feet, a depth of 5 feet, and the velocity is 3 feet per second. So here this is interesting, is we don't know the flow rate right off the bat, but we can find it pretty easily because we've got the area is 50 square feet, and we know the velocity is 3 feet per second. So of course Q equals VA, And then therefore the lowercase q is the flow rate divided by the width. Okay, so it's contracting, and we want to know here what's the minimum width that could be used to avoid choking. So just in the same way that there's a maximum delta Z, there's also a minimum channel width that you can use before choking occurs upstream. Because the narrower that channel gets, you're getting closer and closer to the condition of minimum specific energy. So what we're going to do here is first of all calculate the specific energy at 1. So that is the depth plus the velocity head. And then for this, let's just neglect any expansion or contraction coefficient. Let's just say that that the energy at 1 and the energy at 1 equals the energy at 2 without any C value being accounted for. So find out what would be the critical depth Y sub C if it's flowing at the minimum condition. So it's basically you're saying find the YC that corresponds to 2/3 of the energy at 1. And then once you know the critical depth at location 2, then you can find the velocity, the area, and the width. So this is kind of a little bit of a puzzle because we're looking at this in a different order than we have before. But basically calculate E1, find the critical depth from that, and then you can find the geometric parameters of the channel at 2. Okay, we're just down to 3 minutes remaining for class. Let me talk you through what we do for this contraction. Okay, so the channel is getting narrower. That is increasing the flow per unit width. First, we can calculate the amount of specific energy at 1 is 5.41 feet. So that's the depth and the velocity head was 5.14 feet. And we assume that it's flowing at the minimum specific energy at 2 because that's like the narrowest you can get is going to induce that critical flow. If it keeps getting more narrow than that, then it will choke. So we set the E minimum equal to the 5.14. And so what we know is that when conditions are critical, 2/3 of the specific energy exists as the depth, and 1/3 of the specific energy exists as the velocity head. So I've calculated now the critical depth for that narrower channel. It's going to be 2/3 of the minimum energy. So this critical depth of 3.427, that's the critical depth downstream at location 2. Now this next part is just saying the velocity head is the difference between the energy and the depth. Because remember, the energy is in 2 places, the depth and the velocity head. So this is the total energy at 2. This is the depth at 2. And so the difference between the two, which looks like it's about 1.6 feet, that is the velocity head. So we can use this to solve for V. And then once we know the velocity, we've already known what the flow rate was, 150 cubic feet per second. So that tells us what the area would be, because area is Q divided by V. And this is an unusual order. We don't usually solve for an unknown area, but that's what we've just done because we knew the velocity and we knew the flow rate. So that tells us the area, and we know that it's flowing at the critical depth because it's at that point of almost choking. So if it's flowing at the critical depth, then that means the width, the minimum width that can be tolerated is 4.17 feet. So initially, remember, it was at a width of 5. We can neck it down to 4.17 feet, but if it gets narrower than that, it would cause pooling upstream because there wouldn't be enough energy to push it through the channel. All right, we're out of time. It's 1:50. Because we've got a lot going on, let me just revisit these announcements one last time. Friday's class is online. We won't meet together in person on Friday. We will be back in class on Monday. But the main thing that's on your plate is finishing up the pipe optimization. If you want to show me before you submit it, I'd be glad to take a look. So feel free to take me up on that. You can call me on Teams or stop by my office. If you want to show me what you've got, I'll tell you thumbs up or thumbs down. I can tell pretty quickly if you've done the right thing. So that's it for today. I'll see you for our virtual class on Friday and in person on Monday.